This recording is on the analysis of linkage mechanisms, the second chapter for this class. And we're going to look mainly at the 4-bar, the slider crank like in engines, or crank slider like in compressors, or possibly actuation with hydraulic cylinders where there's no full rotation to the link pin jointed to the ground. That is the red color link here. And then we'll study the quick return mechanism, also called Wentworth mechanism, and then the oscillating slide or cylinder incline, oscillating piston mechanism. Many hydraulic systems use it, and then the Scotch yoke we discussed is being able to generate harmonic motion, the pure sine wave mechanically. Okay, so we'll be looking at possibility of links to perform full rotation, that is to act as a crank, and then finding the limit position of the output link or other links, and then looking for locking position if there's the danger of locking the mechanism and prevent motion from being transmitted through the mechanism. Okay. Applications of the 4-bar. The first that we'll be discussing are many. You see here a few of them. This pump jack, it's a 4-bar, so ground joint, crank, coupler, and output link rocker. So continuous rotational input of the crank makes the output link to oscillate. This one too is crank driven, but the crank is floating, so it's an oscillating fan. There's a 4-bar there, but the power is delivered from the fan motor to the actual coupler. Okay, so would be the link. Coupler is the link that is not pin jointed directly to the ground. Brake of a wheelchair, 4-bar linkage, part of a carburetor, engine carburetor design, an exercise machine. There are 2 4-bars on the the crank. This could be also considered a watt linkage that is driven from the middle link. A folding 4-bar mechanism of a shelf, a 4-bar mechanism. This is the watt straight line linkage used on a vehicle suspension. A door closer employing a 4-bar. Together with a wheel, it forms a 4-bar. Let's not forget that. And they are not the only ones. There are very many applications of the 4-bar linkage. In our analysis, so here's a skeleton diagram. We're going to label links and joints. So R2 will be the length of link 2, R3 the coupler, R4 the other link to the ground, R1 is the distance between the ground pin joints. It is the base link. And we're going to distinguish between the in analysis on the existence of crank, the type of input motion that is possible. We're going to distinguish between the shortest of the 4 links and the longest of the 4 links, with P and Q being the length of the other 2. Okay, so you take, say, the min function. We have them in Excel. So you have a group of 4 numbers, and it returns you the smallest, maximum, the biggest of the 4 numbers. Okay, so firstly, so before checking whether the crank fully rotate, we want to know if really you can assemble the 4 links together. So if you're given the yellow links, the gray and the green links separate with holes drilled, and you want to and pins, you want to put the 4-bar together, it's clear if one of them is too long, like any of them too long, imagine it 10 times longer, you cannot put it in place. But how long it can be and still be able to assemble? So this is the question that we're asking first. It has to do with the triangle inequality, and the answer is that the longest link has to be less, at most equal, than the sum of the other links. Okay, or form in that it's easier to program, say in Excel. So you just take the and sum the lengths of all 4 links, and then this has to be greater, at most equal to twice the length of the longest link. And the case where L is too long is illustrated here. So I have P and S assembled, Q by itself. I want to join these two half pin joints and these two. If I have a gap here, then assembly is not possible. Okay. Next, we'll be looking at what is called Grashof criteria, and likewise makes use of the shortest, longest, and the other two links or their lengths. And there's class 1 4-bar mechanisms, also known as Grashof 4-bars or Grashof class 1. And if we have the shortest and the longest link, the sum of the shortest and longest link less than the sum of the other two, or again making use of the sum of the all links, just because it's easier to, again, this equation as well as this one are easier to put in Excel. So if this or this other one, which is equivalent to whole, then the mechanism is class 1, and depending on which link is the ground link, we can have a situation where if the shortest link is pinned to the ground, it can be turned full turn. That is, this is a crank rocker mechanism, so I can turn the full link, the shortest link. The other adjacent to the ground oscillates between limits. You see here the locus of this point. If instead I have the shortest link connected or is selected as the ground link, then all 3 moving links can perform full rotation. This is going to be called drag link or double crank 4-bar. So and the coupler, the blue link, can also perform. It will perform full rotation. All right, and then this would be the a mirror image. Or rather, no, it's not mirror because the red link now is the base, but I have the shortest link occurring to the right, and here too I can drive it full turn. However, the blue link, the one to the left, is the input. Then the rotation of the shortest link pin jointed to the ground is guaranteed only if I have a flywheel in use. And this would be the case of pedal actuated, like the old sawing machine, and they were 100+ years ago. They were using pedal actuated machine tools like scroll saws and spinning wheels that are pedal actuated, grinding wheels. Just go and Google for pedal actuated machine tools. And then if we have the shortest link chosen as a coupler, then the mechanism can function as double rocker. So I can move this to limit position. The other two links would be in line. I can do the same. The other two yellow and gray link are in line. However, I can power one of the floating joints, and I'll be able to drive the shortest link, the coupler, this time full turn. And this would be the case of the oscillating fan mechanism. You realize it's missing a pedestal, it's missing the fan itself. Motion is collected from the electric motor rotor via a worm wheel gear reducer. Those of you that have this kind of room size, this is more like industrial size fan. There's a knob you can pull, and you can disengage. If you push it down, you engage the oscillating feature. So that's a little coupling there. So motion from the electric motor rotor reduced to a few tens of RPMs. It's causing that floating shortest link, the coupler of the 4-bar, to rotate, and the one is the I'm here. So one is the fan body, and then the other one is the visible link in this picture. And so yeah, it's how you get the oscillating fan working. All right, so these were the class 1 4-bars. The class 2 4-bars, where the early equation is inequality rather is reversed. So instead of shortest and longest being less than the sum of the other two, I have it shortest and longest are bigger than the other two. And of course, assembly is possible. The very first condition that we looked at, where is it? Assembly requirement. Then that's a class 2 4-bar. Equivalent, making use of the sum of all 4 links, easier to program in Excel or in a programming language, would be twice the shortest and longest lengths of the links. If it's greater than the sum of all links, then that's a class 2 or non-Grashof 4-bar. And there's a crank, no link can be driven full rotation, so this can operate only as crank rocker mechanism. And then the limit case is where I have equal sign. So this will be a change point 4-bar. So there are change point configurations. You see here a parallel linkage, the other one being the deltoid or Galloway 4-bar. And so this will be the branching configuration, and the mechanism can continue to operate like the blue link staying, and all links staying parallel with themselves as the mechanism operate or functions. Or it can flip, and I can have continuous rotational input, but the output oscillates. With the deltoid or Galloway mechanism, there will be the blue and the red link are equal, the dark link and the ground link are equal. This mechanism has the unique property that I can perform 2 rotations of the shortest link, and the crank does just 1 rotation. So could be used, although there is no linear input-output correlation. I could use this as a reducer or transmission ratio of 2 to 1. Okay. let's see. I could go to so on Blackboard there is animate GIFs of various mechanisms. I provided here a link. These are my Wikimedia Commons uploads, and I do have 4-bar mechanism listed. We'll go back to this. It shows the limit positions when when discussing limit positions. So let's see. There's a combined image. Okay, so we're talking about the change point 4-bar. Okay, so this remains parallel linkage. This flips, so continuous crank input, oscillation, crank input, crank output, like you see in locomotives, for example. Here are the 4 inversions. This would be are in different order that you saw in the notes. So there's the crank rocker mechanism. Let's look at this one. So continuous rotational input and oscillation to the output link. I have now the shortened, and you can see the link lengths. So 1.4 is the shortest, 1.4 is the longest, and P and Q would be 1 and 1.2. So 0.4 shortest, 1.4 longest. So crank, the shortest link, fully rotates. Here I have the shortest link is the coupler, and this can, if driven from the ground, can be just rocker. You can see the limit positions where the 2 links are in line, 0.4 and 1.4 length. Here it's the case where it's the mirror image. I have the rocker case. The input is the 1.2 length link, and you can observe the limit position. They are in line. In the mirror case, you'll see it has a meaning. It's a matter of having a minus or plus in front of some square root but that will be for chapter 3. And this is the drag link mechanism. All 3 links perform full rotation. The coupler including, you can see if you watch it, it too performs full rotation. Anything else? I believe I do have one where the simulation uploaded where the coupler is driven full turn, full rotation. If not, there's of course a possibility to go to the Wikipedia. 4-bar, it might be there or easier to find. So this is my upload. We looked at this one, and then this is the slider crank, not discussed here. Okay, let's see. Yes, I was looking for this one. So this would be the, like in oscillating fan, I have this floating pin joint being powered. You can see the motor symbol, and it does or drive is in full rotation, the shortest link. And you have the drag link with a rotating coupler. I'm sorry, not drag link, but rocker with a rotating coupler with input from the floating coupler. Okay, so it should be among these here. Cannot seem to find it. If not, you go to the 4-bar webs or article, Wikipedia article. So that was about the 4-bar. Conversation is extended in textbooks elsewhere, discussing the folding 4-bar mechanisms. There is a relatively recent increase of interest in the folding mechanisms in general. You can have deployable structure. It can go on space applications. But one, it's shown here, so this is an in-between position. It can, in horizontal, this side table, the links are in line, 1, 2, 3 joints in line, and it can fold to where it's vertical, the table, the folded position. All right, let's move to the next paragraph on slider crank. It's amazing. The new working model allows you to see the animated GIFs in motion. Maybe I should take advantage of this. So, what do you see here are several application of the slider crank or crank slider mechanism. So slider crank like in engines, crank slider like in compressors. So this is a 4-stroke engine. This is a pump. This is a table with foldable legs. It's possible to, or you can lock the legs in vertical position and then fold it. This will slide along. This one here is a compressor that you can attach it to the power takeoff of a tractor. It's a chain. You need to hook this chain on a stationary part of the tractor. The hose comes from the bottom. There are valves. This is the piston. As it operates, the cylinder moves. So the cylinder does not stay stationary. This is used in a different inversion as this one. And this last one, it shows a oscillating cylinder steam or compressed air engine. So back to Blackboard, if you go to animated engines, it's one of those here. Might be on the second page. Maybe. Click on engine, see how it works. Okay, it's this one. But they overdrew the oscillating steam. They overdrew the flywheel. But yeah, you can see the cylinder oscillating, and by doing so, it gets connected to either the source of high pressure or low pressure. Could be again steam, or could be compressed air, compressed carbon dioxide. Okay, so here too we would be interested in knowing what's the limit in link length. So generic drawing of a slider crank. Slider moves along a line parallel with the x-axis. We're having crank length R2, coupler length or connecting rod R3. R1 is the eccentricity. Many applications of the compressor or engine type, they have R1 very small or 0. Actually, engines, they have it slightly. It's not 0, it's a small amount, and in the direction of rotation of the crank to limit the side force between the cylinder and the piston. So for the mechanism to exist, I have to have R1 be less than the sum of R2 and R3. You can imagine the limit case where the two are equal, so I'll have I'm moving the line of sliding further up until these two links are in line, and there's nothing I can, just maybe due to some clearance, a little bit of motion left and right, which is actually this configuration. So R1 is the maximum possible. Any bigger value for R1 does not allow us to put the two links in the slider, put it on its guide together. So that was one. And then desire to have R2 as a crank to perform full rotation. We are going to observe these two inequalities. So I want to have R2 shorter in length than R3, and then I have to have eccentricity to be less than this difference, R3 minus R2. And for the first requirement, R2 being less than R3, you can look here at, so assuming that R2 is longer than R3, I show a family of array of positions. And then this would be the locus of the piston pin, and I cannot draw a horizontal line corresponding to the line of sliding of the piston that it's going to intersect all circles. So no possibility of full crank rotation. If I have the crank, or I call crank R2, so if R2 is shorter than R3, I can repeat the figure. It's not showing R3 though, so, just the locus of the piston pin. So polar array of R2, and then I draw circles, the locus of this point. So for example, for this position we've shown here, I take the rail off and I can perform or rotate and record the locus of the pin. And I have these family of circles. In order for the line of sliding to intersect all circles, it has to be between, or it has to be, the line of sliding has to go like so. No more, the highest can go would be here to intersect all circles. The lowest will be here. And this is justification for the second requirement in order to have full rotation for link R2. Okay, so look for yourself one more time. Try to understand the concepts based on these two figures. The next discussion is on limit positions. Should be positions, and time ratio analysis. Limit positions are minimum displacements of the output link primarily. We can look at limit positions of other than the output link, but usually, most applications we have motor input that is a crank to the ground, not floating, like in the oscillating fan case, and we pick an output, and the output is at the base as well. Think the examples here. Think the oil pump. In the oil pump, I have continuous rotational input. I have the active stroke when the horse head moves up. I'm pulling the rod, the sucker rod, out of the ground. It lifts the oil up. And then I have the return stroke where I'm not doing work. I'm not pumping oil. And on one, I want to know what would be the lowest position and the lowermost position, uppermost position of the horse head, so that I can size the the pump itself and the length of the wrapping cable, the stroke, the angle between the lowermost and uppermost positions of the walking beam. This is called. It will be a function of that is the amount of pump stroke, the amount of fluid that is pumped in one stroke. And then, of course, I would like to have the motor spending majority of time pumping oil rather than returning the sucker rod to its lower position for the next stroke. More obvious in case of machine tools like shaper mechanisms. I think I do have a shaper here. Let's see. Another instance, this would be the needle bar drive of a sawing machine, although I do have a slider crank and a 4-bar. This as a unit is a we call it it's a Watt 2 linkage with one of the pin joints turned into a how do you call it, turning or rather prismatic joint, I'm sorry. And I think, well, I do have another Wikipedia account which bothered some folks, and they banned me from the site, where I do have the quick return. Let's see, animated GIF. Not necessarily. I mean, I'm not the only one that does this kind of. So quick return, and it's we call quick return just this part of the mechanism, and or maybe here is it animated. Yes, it is. So I have the slow stroke. It went back. We'll find my own, and I can project, or maybe let's see, Wikipedia. Linkage mechanical. Maybe it's here. Maybe same business. No, not here. As you can see, all these are me time spent in appreciation to my contribution to Wikipedia. I got banned indefinitely. This is life. Give the world the best you can, even if they punch you in the face. Okay, so let's look at limit positions first. So motivation for it, I hope, was clear based on the pump jack example. Otherwise, you would of course think the possibility of interference other than the output link, all the moving links, you want to enclose them, you don't want to interfere with the enclosure. Sizing the enclosure would be a matter of studying limit positions as well. So here definition correspond minimum maximum displacement of the what is defined as output link, and again our concern is the 4-bar slider crank, the quick return Scotch yoke, and it was also on the list the oscillating slide or cylinder incline. Okay, so and for time ratio, we define time ratio as the ratio between the long time and the short time. We want time ratio greater than 1. So, and usually consider the long, the one stroke, not stroke, yes, the active stroke and the return stroke, time it takes to do the active stroke and return stroke. And we're going to assume constant crank input. So this translates into time ratio as the ratio between the crank number of radians or degrees of crank rotation. Well, if it's 2 pi, it has to be radians, clearly. So crank rotation to do the active stroke, and the difference is crank rotation for the return stroke. Now, given the stroke for forward and return are the same, we recognize time ratio is also the ratio of the average velocities. Okay, so remember this for your assignments. There's a working model tutorial number 4. You need to calculate time ratio of a slider output mechanism. You want to, or I want to see time ratio reported as a number that is greater than 1. Okay, so let's look at the oscillating slide. There's no time ratio defined for this mechanism because it's not crank driven. It's driven from this oscillating slider, the hydraulic or pneumatic cylinder that expands between a minimum length and the maximum length, and would like to know what the minimum angle and the maximum angle of the difference between the two, that is the angular stroke of the output link, is ultimately. And firstly, to be able to assemble it, we need to have this. This is triangle inequality clear. So between S min and S max, I can have a current S stretch of the or extension of the hydraulic cylinder, and I want to S to be all the times less than the sum of the other two. Of course, you look at the limit, and actually this one it's superfluous. It's only the maximum value that can get closer to the sum of the base and of the rocker length. So I could easily take this out. Again, it's superfluous. Okay, if I apply the law of cosines, I'm sure it rings a bell. Go to any source and refresh your memory how a law of cosine is defined. I can, knowing S, or in general, or in particular S min and S max, R1 and R2, I can calculate theta mean, I can calculate theta max. So how do we state law of cosine to find theta mean? I have S min squared equals R1 squared plus R2 squared minus 2 times R1 times R2 times cosine of theta min. And I can repeat it for theta max, and with theta max and I'm sorry, theta max is S max. I was encircling the wrong notations on this figure. Okay, so law of cosine written for the limit positions, minimum stretch, maximum stretch of the hydraulic cylinder. I can solve for the respective angles, and I can calculate then the output link stroke, the one that it could be of concern. For example, I want to actuate with a hydraulic cylinder gate that opens 90 degrees. Well, this one clearly does not ensure 90 degrees. What you can do is to immediate thought is to increase S max, reduce S min, have theta min a little bit less, theta mat a little bit bigger. See if we gotten the desired 90 degrees. We'll see later on. We'll learn how to size this and also satisfy additional functional requirements. For the Scotch yoke, this is a schematic of a Scotch yoke that uses a pin and a slot joint rather than a block that slides. And the limit positions occur as drawn here when the crank angle is 0 and it's 180 degrees. So these are the limit positions of the Scotch yoke. And it means the time ratio is always going to be 1. It means that the linear stroke of the Scotch yoke is going to be 2 times crank radius, 2 times R2. The quick return, the one that I was looking for an animated GIF. The quick return is an inversion of the slider crank. With crank input, the slider is floating. This one here, it's also an inversion of the slider crank, but the slider is floating. The Scotch yoke mechanism, this one has, it's a mechanism by itself. It's not an inversion of the slider crank. And again, we can have it as a rotation, pin joint, translation, translation. So we have 2 prismatic joints in a Scotch yoke. Firstly, how do you get the limit positions? Well, they occur when the crank is perpendicular to the output link to the rocker, and it's one more thing we have. So other than the crank length, we have the base link, the ground link length R1. If R2 is greater than R1, then this will be a drag link mechanism. So the output link will also perform full rotation. As used in machine tools like in shapers, yes, and primarily, yeah, shapers, then the crank is less than the crank length is less than the ground link. And I said that the limit positions occur when we have the angle at this pin joint, floating pin joint, 90 degrees, as well as here. We recognize some angle equalities. So I have the angle here is the angle here because they are two triangles with mutually perpendicular sides. I have this perpendicular to this and this perpendicular to this. So this angle and this angle are equal. Because of symmetry, I also had this angle, it's also theta min. And this angle would be equal to this angle. The line of centers is bisector to this angle formed with the output link in the limit positions. Okay, so using right angle trigonometry, we can say that sine of this angle here, all right, which is pi over 2 minus theta min, is going to be R2 over R1. And then we recognize that theta max, as shown here, is just going to be pi, the full, like pi angle, minus this angle, which is equal to this angle. Why are the two equal? it's again or because of the symmetry, mirror image, whatever. So we've got theta mean, we've got theta max, delta theta, as you can see, after simplifying a little bit, combining the two equations, will be pi minus 2 r cosine of r2 over r1. And it's expected, does not depend on the size. Angular properties do not depend on the size, depend only on their relative size, so the ratio of the two link lengths. And it makes sense. If I measure R1 and R2 in millimeters, I'll have bigger numbers here. If I measure R1 and R2 in inches, smaller number, but the ratio is the same. If you scale up a mechanism, its angular properties are not affected. Angular motion properties are not affected. As for time ratio, this might be the reason why time ratio is discussed to begin with. Again, this being used as a machine tool, and you have the active stroke, the corresponding the crank going between this position and this position, assuming it's rotating counterclockwise, and it's when material is removed from the workpiece, and then the return stroke is not active stroke and not chip removing stroke, so no productivity there, and you want to limit it, make it short. Okay, so time ratio equation, it's going to be, I have delta theta 2 divided by 2 pi minus delta theta 2. Why is that? Because delta theta 2 is the crank angle for the active or the slow stroke. It's more convenient here to work with, or rather assume delta theta 2 to be 2 pi minus theta mean taken twice, and we figure out theta mean earlier, this equation. So this is what it is shown here, and r cosine, again, you would have to match the pi radians with the r cosine function on your calculator. So if you work on degrees, you need to replace this with 180. So yeah, this is the equation for the time ratio. Again, it depends on the ratio of the crank to R1, the base link. If I have R2 bigger than R1, then the r cosine function has no meaning, because the argument of r cosine function has to be in absolute value less than 1, that is between -1 and 1. So a number that is greater than 1 here renders senseless the time ratio, and that is only because for that arrangement I have, as the crank rotates, the output link also follows. It's a drag link mechanism, also rotates. In the position time ratio of the crank slider mechanism, alike in a compressor as well as some machine tools that use slider crank as the basic mechanism. For example, shapers to cut keyways. Some milling machines come with an adapter that can be attached, and you can machine keyways, for example. Alright, so this is shown in the limit position. Please note, limit position occurs when the two moving links are in line, and the other limit position where the links are overlapped and the joints are inline. 1, 2, 3 collinear, 1, 2, 3 collinear. The R3 is overlap, or R2 and R3 are extended. And we define the minimum maximum displacement of the slider as shown. So I have some right angle triangle. This will be a 90 degree. It's the way it's selected. There is no x and y axis, but this is assumed to be the vertical axis, horizontal axis, or horizontal axis. So how do we calculate S min or S max first? It's simply R2 plus R3 squared together minus R1, the eccentricity, square rooted, right angle geometry. For S min, I just take R3 minus R2 and square it, subtract R1 squared, take the square root, gets me S min. So I have S min and S max. For the time ratio, you look here and see that the slow stroke, the delta theta 2, that is greater than pi half the turn, it's made of 180 degrees plus this angle, which I can calculate as the difference between alpha 2 and alpha 1. Where do I get alpha 2 from? It's from the same right angle triangle. Okay, so I have arc cosine, or cosine of alpha 2 is going to be R2 plus R3 dividing, or should have said R1 divided by R2 plus R3 to get alpha 1 that I'm going to subtract from alpha 2 to get this angle, which goes past 180 degrees. So I'm using this other right angle triangle, and it's going to be R3 minus R2, or again R1 divided by R3 minus R2. So all these explain here, definition of time ratio, and then using alphas, and there you have it. If R1 is 0, then as you can see here, if R1 is 0, then I'll have alpha 1 is 0, I have alpha 2 is 0, so time ratio is going to be 1, something that we expect. A centric slider crank, for half a turn I do the stroke from the away stroke, and the other half a turn would be the return stroke. And finally, the four bar mechanism. You see it here, crank driven, will be that case that we consider, and it's when, of course, time ratio makes sense. I have crank input, and the limit positions, again, same as for the slider crank, occur when the R2 link and R3 link are extended and the corresponding 3 joints are in line. The other one would be where the 2 links overlap and the 3 joints are collinear. And how do I get the angular stroke? Well, I'm using, in a sense, similar to this, well, more for the latter part, for the time ratio, but I'm using the Love's cosine. And for example, in this triangle with red, I can calculate using the Love cosine this angle, which is 180 degrees minus theta min. So law of cosine tells us that R2 plus R3 squared equals R1 squared plus R4 squared minus R1 times R2 times 2 times cosine of would be pi minus theta min. Okay, and so that was for the theta min angle. Theta max angle, I'm applying the law of cosine in this triangle where I have R3, this piece is R3 minus R2, I square it and say that's equal squared, it's equal with R1 squared plus R4 squared negative 2 times R1 R4 times cosine of pi minus theta max, all being stated here, or rather earlier. And then the difference between the two gives us the angular stroke of the output link. If I want to calculate time ratio, I recognize that delta theta 2, same as for the slider crank, is made of 180 degrees, or pi, plus this angle, which is the difference between alpha 2 and alpha 1. How do I get alpha 1 and alpha 2? I apply the law of cosine in this triangle for the red triangle for alpha 1, in the blue triangle for alpha 2. Again, take the difference between the two, add it to delta, to rather pi, to get delta theta 2, and implement this equation. Okay, so this was for the 4-bar. In general, if we have a mechanism with we can analyze and we can generate the input-output functions, we have them here. So shown in red, and this is for a 4-bar. You're going to do this for working model 4. You're going to look at the output graph and extract some values from the graph. Here they are shown directly by the program that I use to make the plot, so it automatically labels the minimum maximum. If not, if they're not available, you need to read them on the respective axis. Okay, so this is output angle. This is, we haven't discussed it yet. This is the transmission angle. And so I have displacement, I have velocity, and I have acceleration. Since velocity is derivative of displacement, where velocity goes to 0, I have limit positions, minimum, maximum displacement. So limit positions also coincide with 0 velocity. It's where the direction of velocity changes, so it goes from negative to positive, from positive to negative, through 0, so that's the limit position. And of course, acceleration is the time derivative of the velocity, and where I have a maximum velocity, I have 0 acceleration. That's expected. And it's one way of verifying if you're to, and you will for your project, by hand derive the velocity and acceleration, displaced velocity and acceleration equations for slider crank used as a punch press. The immediate way of checking their correctness is to look at the graphs and recognize they follow this rule. The velocity goes to 0 at the limit positions, and where I have minimum maximum velocity, I have 0 acceleration. And with the numbers here, again, I read first number is x coordinate of this minimum. Second number is the actual value at the minimum here. Theta 2 at the minute maximum, the actual value of maximum. And you know, the angular stroke, the difference between 255.9 and 40.1 essentially would be the corresponding range of theta. And then for time ratio, you look at the graph, and a delta theta 2 would be this distance, or 135.5 minus 75.1. So that's delta theta 2. And time ratio, you need to divide that by so 360 rather than 2 pi if we work in degrees. Remember not to make that mistake. In general, we expect time ratios for common linkage mechanisms to be less than 2, and make sure that your calculations are such that the number it's greater than 1. If you somehow get a number that's less than 1, you need just take the inverse. So for example, if I take 1.497 and take the inverse, this will be 0.668. But if I want to report the one we agreed as a number greater than 1, you just take the inverse 1 over x. Okay, so this was it for limit positions and time ratios. Remember, you're going to do this something similar to this, working with a plot. You need to inspect the values to look at the minimum and maximum independent variables, values of independent variables, and minimum maximum of the output link, and calculate a time ratio. As for the limit angular stroke, as it is the case here, you just take the difference between what the maximum minimums are. Okay, so I'm stopping here. I'm going to pause this, and we'll continue a separate recording on transmission and pressure angles.